Hello, welcome back to the General Equilibrium Theory of Private Capital Valuation, Lecture 2. This covers Part 2 of the book. Today we'll elaborate on the optimal stopping problem, the closure of the McKean-Vlasov externality, and the augmentation by Hawk's self-excitation. We operate on a filtered probability space under the usual conditions. We've got the sigma, the sample space, F as the sigma algebra of events, Ft is the filtration, and P the probability measure. We assume right continuity of the filtration and completion by the probability null sets. Without right continuity, we'll lose the characterization of stopping times via their debut. Also, adaptiveness is required for well-posed results. Let's start with the value function, which is a Snell envelope and the supremum over f adapted stopping times tau of the expected discounted exit payoff S. By El-Khrou's theorem, the supremum is attained. And then the Bellman equation restates this recursively at each state time point V. It equals the max of S versus weight H and reoptimize. The DPP problem carves the plane into C, the continuation region, and S, the stopping region. The issue is how to locate this free boundary L star. Now, the heat map here shows the exit boundary, which rises over time towards the theta steady state where liquidity is zero in this parabolic domain. Ito's lemma expands dv and dl square collapses the second order term. The bracket over here, dtv minus kappa L minus theta dlv plus the second order term, this basically is the generator, AV. Then we take expectations, which kills the martingale term dw, and then discount and substitute into the Bellman's equation, and then you're left with the boxed HJB, the Hamilton-Jacobi-Bellman equation. This is valid in the continuation region C. So what's happening here is Ito is giving us the generator, the expectation removes the noise, and the discounting supplies this RV term. The HJB equation must sum to zero inside the continuation region. So you've got four different elements: the time decay, which is delta TV, and that's the rate of change of value. Then you have the drift term minus kappa L minus theta DLV, which is the mean reversion in the liquidity state, K times L minus theta over here, and K L minus theta, that piece drags L back towards its long run level of theta, which is zero. The diffusion term, the third term, the diffusion term half sigma L squared delta L squared V. This is the Brownian curvature or the value adjustment from volatility. The Jensen convexity effect is captured by this term as well. So the fourth term, the discount minus RV term, this is the required rate of return, or we can interpret it as the cost of holding the asset. So on the right hand side here we constructively verify the HJB PDE on the continuation region, and you can see over here this dashed line. Okay, this dashed line is 0 by construction, and basically the diagnostic measures local truncation error in any numerical scheme. Now, the boundary conditions. HJB alone is underdetermined. We need, because the free boundaries are known initially, we need two conditions to close the problem. First, we need the value matching condition. We talked about this in lecture 1. On the free boundary, V equals S. That's the continuity of the Snell envelope, automatic by Dub's theorem on Cadillac modifications. The second is the smooth pasting condition. Here, the L derivative of V equals the L derivative of S on the boundary. So the terminal condition is where at maturity you don't have any more optionality, and V equals the realized secondary price, S. On the right hand side, have a look at the smooth pasting condition at work, and you have a correct tangency over here. Okay, but if there is a kink at the boundary, this would be suboptimal, and you can see the kink over here, different slopes of L, and so if you perturb the threshold improves, if you perturb the value can improve essentially. So you do want no kink at the boundary. Over to the HJB variational equality, the free boundary problem is now wrapped into a single object, the Benuson-Lyons variational inequality. Here, it's the minimum of two quantities that would equal 0. So on the continuation region, you have this first quantity, this entire quantity vanishes, and HJB is active, and you have V greater than S. In the stopping region S, you have the second term V minus S that vanishes, and the obstacle S binds us. Now, the free boundary supports a Lipschitz but not a C2 value function. So across the boundary, we have the second L derivative that jumps or may jump. The HJB equation, which is a second order PDE, is therefore not satisfiable classically. So even when the value function is not fully differentiable, we can use the viscosity solution that guarantees a well-defined and stable solution to this HJB equation. And the Barles-Suganidis 1991 theorem guarantees that any monotone, consistent, stable scheme converges to the unique viscosity solution. So here you have the local maximum from the subsolution, and then you've got the local minimum from the super solution. Since both conditions hold simultaneously, we are guaranteed that we have a viscosity solution. So V need not be differentiable. We can use the test function and derive the viscosity solution. Because the value function V may have a kink, may not be classically differentiable, we can use a viscosity solution to replace the derivatives of V with derivatives of smooth test functions, psi or plus and minus. This is due to Crandall-Ishii-Lyons 1992 result. The comparison principle guarantees that the HJB has a unique viscosity solution that's monotone, stable, and consistent. Over to the Kalman-Bucy filter, we know that L is not directly observable. So if your observation system is linear Gaussian, has a linear Gaussian state and linear Gaussian observations, the conditional law of L given the observation filtration is Gaussian. And we get L hat, the mean L hat, and the variance P. The Kalman-Bucy filter is finite dimensional and is a sufficient statistic. We've got an observation model here, and we have noisy linear projections of L. The drift term in the PDE here, or the SDE filter estimate, is over here, and the innovation correction is over here with the surprise and the Kalman gain. Now, the Kalman gain is really the dynamic weighting on the innovation, and it's larger when uncertainty is high or observation quality is good. You can see that if we have assumed the Gaussian state here. Now, if you have non-linearity and a non-Gaussian set of observations in the model, then the sufficient statistic is infinite dimensional. And we land in the Kushner-Stratonovich equation, or the Zakai unnormalized form. If the systems are nonlinear, well, we could use extended Kalman-Bucy filter, which linearizes the nonlinear system locally. We could also use the unscented Kalman-Bucy filter, which uses deterministic sampling methods. Another option is to use the particle filter. That is more general in terms of treating nonlinear and non-Gaussian systems. Here on the right-hand side, you see the Kalman-Bucy filter convergence, and the filter L hat tracks the unobserved true L from noisy observations. Initial diffuse prior contracts as more observations arrive, and the posterior band shrinks to the steady state. And as long as the data are consistent with the Gaussian representation, we are okay with the Kalman-Bucy filter. And related to that, we got the Riccati posterior variance P, which governs the filter's posterior variance P as a balance of three different forces. So you've got the minus 2 kappa PT, which is the mean reversion decay, then the volatility-driven growth, sigma L squared, and information acquisition from observations, that's the third element, P squared H squared divided by R. Okay, and you can see the posterior variance falling very fast as your observation noise. You can see that the sigma is, as sigma reduces, you move inward and the variance reduces quicker. And on the right hand side, you see information versus observation quality. And observation noise is over here, and that's the quality. So as the noise reduces and quality improves, you can see that the steady state posterior variance also falls. In our calibration, sigma is 0.4, and the steady state posterior variance is 0.075. So the implication for HJB is we basically substitute L for L hat, the unbiased efficient estimate for L, and the free boundary L star is in the L hat space. So LPs may have different observation histories and decide to exit at different times, although they face the same true conditions. The Fokker-Planck equation evolves the probability density of L forward in time. The generator L gives the expected instantaneous rate of change of any test function psi. The Fokker-Planck forward operator L star is the adjoint of the HJB backward generator L, and the density flows forward in time in conservation form, dual to the value function flowing backward. Here you can see the Fokker-Planck equation, and we equate the integrals. So starting from a point mass L, the Fokker-Planck density P drifts and diffuses toward the stationary Gaussian, and it reaches precisely the probability current J of LT that vanishes everywhere. So you've got the stationarity of the L point mass coinciding with the probability current converting to zero. As you can see, this moves down to stationarity. So in terms of stationarity, we set dTp equals 0 in the Fokker-Planck equation, and that gives us the ODE whose solution is the stationary density. So stationary density over here, that's the closed form solution, and the value of the variance over here is 0.114 based on our calibration. So the stationary distribution has this variance value, and we have the spectral convergence, which is finite, exponentially converges to stationarity at a rate of kappa, and we have a half-life of 1.54 years. The stationary density is Gaussian with mean theta and variance sigma L squared over 2 kappa. The Bakery-Emery curvature kappa gives the log Sobolev inequality with constant 2 kappa, hence the hypercontractivity of the OU semigroup. And you can see over time how from the initial condition to stationarity we've got the conditional density at various horizons. Let's upgrade the single agent model to a mean field game where every LP's liquidity is coupled through the population. The McKean-Vlasov SDE is where each LP's drift now pulls towards its own long-run level of theta and the population mean as well, with a coupling strength of beta. This is what makes liquidity correlated across LPs. The population mean M, which is the expectation of L, that's the average liquidity state computed from the density P of LT. So we have the coupled HJB backward in time, and the value function PDE now contains M, and also the coupled Fokker-Planck is forward in time, and here this density PDE also contains M in it. So this is the coupled system, and this is the mean field game. Here we show the best response cobweb. So that's a successive set of iterations contracting toward the equilibrium law M star. Under Lazary-Lyon's monotonicity, the iteration is a contraction in the Wasserstein topology on continuous measure-valued paths. Absent monotonicity, the iteration may fail to converge and multiple equilibria can coexist. So this chart shows how we reach equilibrium. Here we show the cobweb iteration, how it converges to the mean field equilibrium, which is the fixed point L star. P2 of R is the space of Borel probability measures on the real line with finite second moment. It's a Polish space when equipped with the 2 Wasserstein metric. The Otto-Villani formal Riemannian structure makes it a non-smooth Riemannian manifold. Why is P2R, the Wasserstein space, the right space for us? Well, the Fokker-Planck flow is continuous in W2. The McKean-Vlasov drift is Lipschitz in W2. Also, the value function is Lipschitz in W2. And we also have the Wasserstein-Arzela-Ascoli result, which gives us compactness. That's what we need for the Schroeder fixed point. Here, we make the Wasserstein 2 distance more concrete. It's the minimum effort cost of transporting one distribution's mass onto another. And it's the natural metric on P2 where the mean field game equilibria live. Closed form for Gaussians. The transport picture on the left over here, as you can see this shift happening, it shows that the optimal transport moves mass smoothly from left to rightward along straight rays. On the right, you can see that W, you can see the contraction rate kappa, okay, where W2 contracts. This contraction is equivalent to displacement convexity of relative entropy. The function space is continuous, set of continuous trajectories of probability measures with uniformly bounded second moment, closed and convex in the Wasserstein topology. We verify the three Schroeder hypotheses. We've got continuity, we've got self-map, and we've got compactness. Now, if we don't assume sort of these three conditions, the alternative is Kakutani for set-valued phi when optimal stopping is non-unique, or the monotonicity-based existence theory of Cardelier-Hadikhan-Lu 2017 result, which avoids compactness arguments in favor of monotonicity contracting in W2. So let's have a look at the three Schroeder conditions for fixed point existence. The compactness, basically the parabolic regularity of the Fokker-Planck equation basically smooths out density over time. Plus, we've got the Wasserstein-Arzela-Ascoli theorem, where a family of continuous functions from a compact space into a metric space is precompact. Every sequence has a uniformly convergent subsequence if and only if it is equicontinuous and pointwise bounded. In terms of continuity, we have continuous dependence on the coefficients in the case of both HJB and the Fokker-Planck equation. That means that phi is continuous, and small perturbations in input parameters result in small continuous changes in the solutions in HJB and FPE. In terms of the self-map, for M large enough, we've got phi of M contained in M. And the fixed point of phi is the mean field equilibrium. In terms of the Schroeder iteration, the three Schroeder conditions are verified by standard parabolic regularity for FPE. And as discussed, we are combining that with the Wasserstein-Arzela-Ascoli theorem for Boli-Villani for compactness and continuous dependence of HJB and FPE on coefficients in W2 for continuity. Finally, under Lazary-Lyon's monotonicity, the iteration contracts at a geometric rate proportional to beta kappa t. And you can see the geometric contraction over here for successive iterations and the existence of the fixed point through iterating the best response map. You can see the successive shifts of the probability distribution. So Schroeder then gives us existence. In terms of uniqueness, suppose for contradiction, okay, two solutions, V1, P1, M1, and V2, P2, M2. We have the deltas here. And basically the strategy is to test the HJB difference against delta P and delta V. We integrate it, we test the FPE difference against delta V, integrate. The Lyon's duality identity then cancels the volatility cross terms. What remains is a single cross term arising from the McKean-Vlasov coupling. Uniqueness is established because the squeezing forces all the differences to zero. So Under Lazary-Lyon's monotonicity, the cross term is non-negative. By the same duality, it is also non-positive. So the cross term vanishes. This is the squeeze. That's the squeezing argument over here. Now the Gronwall on the sum of squared norms gives delta V and delta P identically equal to 0, and uniqueness is the appropriate function space in W2 pointwise on the parabolic domain. Monotonicity rules out the strategic complementarities that produce the self-fulfilling multiplicity. Non-monotone extensions, however, will admit multiple mean field equilibria. Look at the right representation over here. Non-monotone coupling, you've got three equilibria. So non-uniqueness is possible. But if we assume the monotone coupling, we've got the unique equilibrium. Now, the master equation, it's the deeper unifying object. The mean field game gave a coupled system of three objects on three different spaces. We have value V, density P, and mean M. This master equation collapses all of these into one function U of L, M, and T. It's defined on the state space, the measure space, and the time domain. The master PDE has three pieces: a time derivative, dtu, the state generator, LLU, and that's the usual drift and diffusion in L. And then we have a measure derivative term. That's the Lyon's derivative, du dm. And that's integrated against the Fokker Planck operator. Du dm is the Lyon's derivative. That's the analog of a gradient on Wasserstein space. So in the case of an n-player game, we see that it converges to the mean field game as n approaches infinity at a rate of the order 1 divided by square root of n. That's the propagation of chaos. Here, the mean field game gives this coupled system, three objects in three different spaces, as we've discussed, and we collapse everything into this master equation. And we've talked about the Lyon's derivative du dm. Okay, so let's move on to the flow of the master equation. Here we've got two different representations, one for the single agent and one for the population law. In both cases, you see the liquidity state and the population mean converging to the equilibrium. Now, it's a phase portrait of the master flow projected onto the joint state mean plane. Trajectories from arbitrary starting conditions converge to the equilibrium pair L star M star. If we assume monotonicity, the equilibrium is locally exponentially stable. The linearization has spectrum in the open left half plane. So we talked about the propagation of chaos. The n-player game converges to the mean field game at rate order n to the minus half in the empirical measure topology. The trajectories you can see are converging to the MFG equilibrium over here. Now, the intensity, the Hawk's self-exciting intensity, lambda of t, it starts at a baseline, lambda 0. That's the baseline. And it gets a bump from a bump alpha, okay, from each past jump. And then it decays exponentially. The mean intensity, ODE, mu of t, is the expectation of lambda. That follows a simple linear first order ODE. That's shown over here. Now the branching ratio NH is equal to alpha divided by beta of h. That's the expected number of children jumps triggered per parent jump. So the stability condition is where nh must be less than 1. That's the subcriticality required for stationarity. In our calibration, nh is 0.56, so very much in the subcritical region. And we've got the augmented generator over here. 3 terms. We've got the drift, the diffusion, and the jump integral. The jump distribution has a mean of negative 0.28 and a variance of 0.12. Let's have a look at the graphs over here. The Hawk's intensity equals a baseline lambda 0, as we discussed, plus the integral that sums the exponentially decaying influence of every past event. So the each event raises the conditional probability of the next event. You can see the clustering of events or crises. In this chart, you see Hawks above and Poisson below. Here there is no memory, same rate. Here you have clustering of events. So self-excitation creates these clusters. In terms of the branching ratio, you see that we are operating over here, 0.56. As it moves towards 1, it becomes more and more unstable and explosive. So supercritical region over here. We are very much in the subcritical region. And then on the right, this is the Hawk statistics. We are comparing Hawks versus Poisson. And you see the Bartlett spectrum falling very fast in terms of the excess low frequency power. So the dashed line is the Poisson flat line, and you can see how the Bartlett spectrum falls very fast in the case of Hawks. Now, Hawk statistics here, it shows that it is actually pretty well aligned with the counting process. Now, let's move forward into a sort of a view of welfare. So private versus social welfare. Each LP picks, in the case of private welfare, each LP picks its own stopping time to maximize its own discounted payoff. It treats the population mean as exogenous by the Nash hypothesis. But the social planner, okay, this is the private problem. The social the social planner's problem is to pick the entire family of stopping times to maximize aggregate welfare. And that should be subject to the joint McKean-Vlasov dynamics. The planner internalizes the McKean-Vlasov coupling, and dm d tau is not 0 as far as the planner is concerned, but it is 0 as far as the private individual or private institutional investor is concerned. So LPs ignore this this externality, but the planner does not. And you can see in the right, the social value is higher than the private value, and any specific liquidity state. And then this welfare gap is what we are going to convert, this deadweight loss. We are going to convert it into the Pigouvian tax. So the Pigouvian internalization goes something like this. So one LP's exit moves the mean of the population, MT, by order 1 over n. It's tiny individually, but it propagates to the entire population. Okay. Through the McKean-Vlasov coupling, this shifts every remaining LP's drift by minus kappa beta delta m. Okay, that's the drift that impacts all the remaining LPs. The aggregated and discounted externality on value is delta log v. That equals minus k kappa beta delta mt times the remaining time to maturity. So how do we address this externality? We have this closed form solution. That's the Pigouvian tax equals beta sigma L squared over 2 kappa squared. And here it's interesting because when L is positive, you've got, L is positive over here, and you've got zero tax, zero Pigouvian tax. But as L becomes more and more negative, the tax increases to address this externality. In terms of calibration, the parameter values we've used for baseline calibration, beta 0.15, sigma L 0.32, kappa 0.45, and theta 0, that gives us a multiplier of 0.03793 in terms of the tax rate, the Pigouvian tax rate. And in deep distress, negative 1.5, the tax rate is 5.69% of NAV. Calibrated to empirical data, we see that the empirical observations with the fitted OU model, it gives us the parameter estimates, all the 4 parameters, sigma squared, theta, sigma L, as well as kappa, in specific ranges. So we've got kappa 0.45 plus minus 0.06, sigma 0.32 plus minus 0.03, theta is 0, and sigma squared, the stationary variance, is 0.114 plus minus 0.02. Asset class differentiation through beta. You can see different asset classes, and that will represent different Pigouvian taxes as well. Now, if you have a portfolio, you do a weighted average of, in a multi-asset portfolio, you do a weighted average of the value of your portfolio times the asset-specific Pigouvian tax to derive the portfolio tax rate. And the valuation of your portfolio will be adjusted accordingly. Here you see the $100 hypothetical value of a portfolio pushed up by the Jensen correction, and then pushed down by the equilibrium rate correction. And then that gives you your value, where that's about $37.90, huge discount on DCF. But this is, of course, assuming a global financial crisis level of depth. This is a representation of a three-dimensional representation of the LAV value versus DCF value, that ratio. And as the liquidity state improves, you can see that the valuation improves. And we have also taken into consideration the crowd coupling beta over here. The chart on the right, it shows the LAV to DCF ratio again, and you've got horizon. As the horizon increases, the effect will also be more significant when you have a distress situation. So here we have assumed L equals minus 1.5, so a global financial crisis level of disruption. And so by different asset classes, all different asset classes keep losing value as the horizon increases. Now the master equation, it admits a unique C11 classical solution on R cross Wasserstein cross 0 to T. The Lyon's derivative is the Hilbert tangent gradient on Wasserstein space. The equilibrium is the unique critical point. Cardillige, Sirant, Poretta 2023 extends regularity to common noise. Bertucci treats the mean field game with absorption directly applicable to our optimal stopping formulation. The selection is non-monotone in this case, in the case of the mean field game. The selection problem is something that we need to discuss. Under Lazuli-Lyon's monotonicity, our mean field game is unique, but if we drop the monotonicity assumption, we see a pitchfork bifurcation appears. And in the non-monotone coupling scenario, have a look here on the left, we've got two stable and one unstable equilibrium. So we've got three equilibria. That is obviously not unique. So if we have multiple mean field equilibria under non-monotone coupling, we can use the vanishing viscosity selection method by Bertucci and Lyons. And you can see that in this case, unique and stable equilibrium is not guaranteed in a non-monotone setup, but the vanishing viscosity selection method for the unique and stable entropic mean field equilibrium may be possible even in a non-monotone MFG. Okay, so it can potentially possibly reach a equilibrium that is unique under the entropic MFE condition. So the mean field game of optimal stopping is treated by Talby, Tozy, Zhang, 2023, and this is a consequential recent development for our framework. It gives us the first rigorous theory of mean field games with optimal stopping controls. So our framework, if properly understood, is really this TTZ solution as a relaxed equilibrium, adding on the McKean-Vlasov coupling. So not necessarily it has to be a point solution. It could be the relaxed equilibrium could be a probability distribution of stopping times, not necessarily a point solution. Now, rough liquidity beyond OU Markovianity, empirical volatility is rough, and that's shown by Gathrel, Jason, Rosenbaum, 2018. The log volatility increments exhibits Hurst exponent approximately 0.1, far below 0.5. The same diagnostic applied to secondary market spread series gives a Hurst of approximately 0.15. That's also rough. So if liquidity is rough, our OU model is misspecified. L is not Markov. The autocorrelation decays as a power law rather than exponentially. The correct framework is a Volterra stochastic differential equation with a rough kernel. Now, the Hurst should be between 0 and 1/2. You can see under rough volatility, the sample paths can diverge. The autocorrelation function can decay unpredictably. And so with irregular sample paths and unpredictable autocorrelation structures, we lose the stable structure for forecasting, risk management, or pricing. The Volterra SDE would have a long memory with kernel K and Hurst exponent between 0 and 1/2. L is no longer Markovian, you're in the fractal dynamic space. And HJB becomes a path-dependent PDE. Near critical Hawks, presented by Hardiman and Bouchard 2014. The empirical equity markets calibrate to a Hawks branching ratio of 0.95 plus or minus 0.02, extremely close to the critical line of 1. It's operating extremely on the edge here. But in the private market calibration, that's sitting at 0.56 over here, deeply subcritical. So our framework is well posed. But the empirical near criticality signal in equity-related instruments feed into secondary market pricing through arbitrage relations, which means tail correlations are stronger than our subcritical estimates suggest. Bifurcation structure of the mean field equilibrium in our parameter space. This phase diagram plots beta against horizon t. And you can see that the bifurcation locus is presented here. The Lazary-Lyons monotone regime delivers a unique mean field equilibrium above the locus under non-monotone extensions. A pitchfork bifurcation appears here, where you've got crowd coupling beta values increasing. Our calibrated asset classes sit at distinct positions in this diagram, and you can see equity beta at 0.8. We have assumed t equals 12 years. This is closest to the bifurcation locus, and that is shown over here. Okay, so stable mean field equilibrium is represented over here with a high exit probability, and here with a low exit probability. And in this area, the mean field equilibrium is unique. And when you're operating over here, you have equilibrium population mean is 0, and you have an unstable MFE. So the selection of equilibrium becomes empirically relevant. The Fokker-Planck equation is a gradient descent. The distribution is always rolling down on a free energy landscape where the energy is relative entropy and the geometry is Wasserstein. The JKO theorem, the Jordan-Kindle-Lehrer-Otto theorem 1998, makes this precise. The Fokker-Planck flow is the gradient flow of relative entropy with respect to Otto's Riemannian metric on the space of probability measures. The left panel here shows the JKO scheme in action. You build the solution in small steps, each one balancing stay close to where you are measured in Wasserstein distance against lower the free energy. A bimodal starting density relaxes smoothly into the stationary Gaussian. Okay, so stationary Gaussian is shown here in green, and there is a lot of iteration that leads to it. The stationary equilibrium, the stationary density. Now, on the right, you see the monotone decrease in free energy as we increase the iteration steps. So, free energy, which represents the relative entropy plus some regularization, it descends at a rate of 2 kappa. That's equivalent to the Bakery-Emery numerical scheme. Here we draw the sharp distinction between two superficially similar problems. The left side shows the mean field game, that's decentralized, and each LP is independently picking its optimal exit tau star to maximize its own value, treating the population distribution M as fixed. The equilibrium is a Nash point, phi of M equals M, and everyone best responds. Nobody internalizes their effect on others. On the right, we see the mean field control. That's the centralized social planner view. A single social planner picks all the exit strategies together to maximize aggregate value. fully accounts for how each decision moves the population mean m to m of tau. Now, these two solutions are not the same. The gap between them is exactly the Pigouvian wedge, the welfare loss from agents not internalizing the McKean-Vlasov externality. The mean field game from Nash underaccounts for the collective cost. The mean field control MFC of the planner, the optimum we get there is what the Pigouvian tax is designed to restore. Our mean field game is a continuous time heterogeneous-agent macro model in the tradition of Ayagari, Bucy, Huggett framework recast by Ashdow, Hahn, Lazary, Lyons, and Moll in 2022. The structure is identical: a backward HJB for each agent's policy, a forward Kolmogorov equation for the population. They're coupled together, exactly our forward-backward system. The dictionary just renames the pieces. Their wealth state is our liquidity state. Their population distribution is our population mean. The one real distinction is the corollary. Standard Krusell-Smith couples agents through prices. Ours couples through the population liquidity state directly via McKean-Vlasov. That's what makes it a true mean field game. This slide is the engine room, how we actually solve the master equation. So the problem is that the master equation lives on Wasserstein space, which is infinite dimensional, so finite difference and grid methods die from the curse of dimensionality. Deep BSDE escapes that. It reformulates the PDE as a backward stochastic equation and trains a neural network to learn the solution at a cost that doesn't blow up the dimension. The convergence plot, as you can see here, it makes the point. The finite difference and semi-Lagrangian methods stall at low dimensions, while the deep BSDE keeps converging. We make it concrete by replacing the infinite dimensional measure with its empirical version m hat n and parameterizing the value function u with a network. This is what turns the master equation from a theoretical object into something we can actually compute. So that concludes lecture 2. Our framework is now complete. Let's quickly look at what we've done today. We've constructed the LP's optimal stopping problem under McKean-Vlasov coupling. We've derived the HJB obstacle problem rigorously. We've formulated the viscosity solutions, established existence via Schroeder and uniqueness via Lazary-Lyons monotonicity, augmented with Hawk's self-excitation, and closed the externality wedge with a closed-form Pigouvian tax. The asset class hierarchy of liquidity discounts is now a theorem, not a stylized fact. Thank you for your time today.